Morning, everybody. Time to get started. I know I'm starting a little early, but I thought there might be some audio problems. Let's actually wait a little while. We can actually listen to this, yet again, the same royalty through music for a bit. Actually, I'll be back in 1 minute when we actually start. Is there audio problems? I don't know. Doesn't look like there is anymore. It's because the headphones were plugged in. That was weird. I don't get what happened when those were plugged in. Well, anyway, let's go ahead and get started. Turn off the music. And then come to me. Good morning. And how's it going? Looks like the sound's working. Good morning from a soon-to-be hot and sunny Santa Cruz, California. We are about to get a heat wave today, and a real one, like in the 90s and stuff. Sometimes we talk about heat waves being 75, 80, but no, we're talking like in the 90s and hot and heat wave advisory. And there was no marine layer this morning. There was nothing but straight up sun right away, and it didn't cool off that much last night, so I'm not pleased. Today's tea is brought to you in my new mug, celebrating half of my Jewish roots, my Ashkenazi part, way they. I didn't grow up with much Yiddish in my house from my mom. Anyway, tea is a turmeric detox, which we should all do. I don't really know if we should all do it, but I'm doing my turmeric tea this morning. It's lovely. Today we are going to be covering indexes in PostgreSQL. So, was there anything else I needed to talk about? Oh, Doom Patrol. I'm upset with all of you for not telling me about Doom Patrol earlier. Oh my gosh, what a great show. I cannot recommend it. My kids and I are just making it through season 1 right now. I cannot recommend it highly enough. It is such an awesome show. Oh, so good. It's a superhero show, right? Don't get me wrong, but it's kind of like some of them are anti-heroes. Some of them are but the creativity and the way that whoever does the graphic novel that they're adapting it from really did some really funny ways of making up characters, and it's just really good stuff. Really, really good stuff. Emotional at the same time. I was crying the other day during one of the episodes. All right. Done. On to indexes in PostgreSQL. Let's do this. Okay, so today, let's switch to my normal. Boop, there we go. So what we're going to be doing today, again, is from learn.crunchydata.com. Right, that's where we are. We're under, well, let me go all the way back. So under learn.crunchy, no, that's not what I want. Let's go here. Learn.crunchydata.com. Right, so that's the top level. And then you're going to go to application developers, then basics for developers. And then we have an introduction to indices or indexes. Oh yeah, I promised I would come down on which one I prefer. The one I prefer is indices. But because that's how you learned it. That's proper English. That's how I learned the word indices. Multiple indexes is indices. And if you say that in like the statistical literature, you don't say there's multiple indices, not indexes. God. But for some reason, in common use, we've come to say both indexes and indices interchangeably. And when we put up when Kat and I were writing these catacodas for review, we got a lot of funny looks about writing indices, which me speak pretty English someday. We gave into popular demand and went with indexes. But personally, I am all about indices. So that's what it should be. All right. So when you go into here, What we're going to do is there's the introduction to indexes. Sorry, that's my hybrid. The introduction to indexes is really pretty basic, and it covers B tree, and I'm not going to go into it today because I'll cover most of the stuff when we do this one, which is index types in PostgreSQL. Because the first one we're going to talk about is B tree. I'm going to skip talking about this intro part for now. I think if for part of this, we're going to come back to this. This is about like bindings and operator classes, which is really important to somewhat understand, especially if you're going to go a little bit deeper into indexes or indices. But I don't want to start with it because it's kind of confusing if you don't understand some more about indexes. So I want to put some context with some examples, and then, or maybe actually talk about some of the stuff through examples. And so I'm going to go straight to the first type of index, which is B trees. So B trees stands for balanced tree index. It's the one that most databases use. It's very common, and it comes out of the box. It's the one, if you say, alter table create index or create index blah on blah, this is the one you get by default, right? You get a B tree index, right? If you don't specify anything else, you'll get a B tree index out of PostgreSQL. It's the way you use this, the purposes for it, right? So this is the way almost all of these different types are. We're going to cover 4 different types today. The way this is, the purpose of it is it's just your basic one, and it works really well in most cases, right? So you don't really even have to think about it. So you can ignore, in most cases, you can ignore almost everything else I'm going to say about the different other index types. You can't ignore the caveats I'm about to give you about indexes, but you can ignore most of the other ones if you want, unless you get to the special use cases. So the other thing to know about indexes is they're used by the database for 3 different things. One of which is, and one which most people know off the top of their head, is to speed up searches, right? So an index is kind of like the index in the back of the book, hence the name. What it does is if you have a table full of a bunch of different values and you want to go to specific entries, you go to the index first, find where it's organized so you can find specific values first and pull them back, right? That's the basic idea behind an index. The first caveat I'm going to give you is that, and there seems to be some golden rule that's made up, but it's generally about if there's more than 10% of, if the value you're looking for makes up more than 10% of your column, an index will basically be ignored by the query planner. Because it's going to because random page access, like reading random places on disk where that thing is stored, is expensive, as opposed to going sequentially through disk is faster, right? So if you have to go through and find generally, I mean, this is a rough number, but if you have to generally go around and find more than 10% things randomly, it's just faster to go through the whole table and pull those things out as you come across them, right? So you don't want to index, if you have a table and you're going to be looking up things and it's basically like 1 quarter, 1 quarter, 1 quarter for 4 different things, the index may not help you that much, right? That's the thing around that. So be aware of that, first of all, with indexes. The next thing is indexes help you for searching, right? And then the other 2 operations that many people may not know that indexes can help you with are group by, right? Because if you do a group by, it can help it figure out it can help the query planner figure out where to get the things to group, which are aggregate queries, right? And then the other thing it can help you with is order by, because it knows, especially because the index generally tends to be in order, right? So it can actually help with order by sometimes. But again, those all depend on the quality of your data, the characteristics, not the quality, but the characteristics of your data. The next thing is indexes only help with certain operations. They're not going to, there has to be an operator that actually, so operators are things like you can see, I think you can see over here, right? The greater than, or this is a less than or equal to, equal, greater than and equal to, and greater than, right? For B tree. Those are the main operators, those are operators, and those operators are supported by the index, right? If you try to use an operator other than that, right? Like plus, or what's another index? Well, so I'll give you an example here, right? But anyway, those are actually supported by the index. The B tree will actually help with those. If it's not supported by the index, then the index will not help with the search, the group by, or the order by. So it's important to know what operation you're going to be doing, what operator you're going to use, and that will determine whether the index actually can help you or not, right? Like that's a good first order cut. Okay, back to B tree though. So B tree, it can also work with between and in. It can also work with null and is not null. It can also be used with like queries, but it's really important about something about how you're going to use like. It can only be where you're going to give the beginning part, and then we're looking for like basically, I think it's stem, anything that flows off the back of it, right? Where that it can help with because it can look up the first several characters using the index and then find the other things. But if you put the wildcard in front, then the index won't help at all. And then it gets even more complicated. There's different types, and this gets into something I didn't want to talk about, but the operator classes where you have to just read this one. Come back and read it. I don't want to talk about it now. If you're going to want to use likes with your index, you have to actually pay attention to how you make the index so that it knows whether you're doing a text column, a car column, or a varchar column. Okay. So that was one of the big main points, right? The operators, what it can help you with, those are big main points. The last big main point I'm going to make before we go into some more examples is there's always a trade-off with an index. Indexes are not free, right? So yes, they can offer speed up for certain operations, but that comes at a cost. Indexes, one, eat up disk space. And I know, again, you're going to say disks are cheap, but disk access is not cheap, right? So that's the part where we're getting into where the cost actually is, right? We'll see as we go through these some of the disk trade-offs you make. And the other thing is the way indexes work is the database has to maintain them. So yeah, for reads, there's no cost, necessarily big cost to have an index there. But every time you do an insert or an update, you actually have to update the index as well. So that's why a lot of times if you're bulk loading data, you drop all your indices, you drop all your indices and then you insert your data and then you rebuild your index if it's a really big bulk insert, because it'll slow down your bulk insert incredibly, because every time you insert one row, it has to go update the index. I mean, sometimes you can put it in a transaction and that will slow down that may help some. Except, no, not really. I'll show you why in a bit. But the real thing is to drop them and recreate them, right? So the idea is there's a cost to making an index, and you need to balance whether it's really going to help you with your query versus what the costs are going to be to making it. And we'll go through each of the indices and talk about them today. All right, then show it. So the first one is we're going to actually, I should probably make this a little bit bigger. No, that's not what I want. No. Come on, make the font size bigger. Why are you not being nice? No, I don't want to scroll. There we go. All right, that's probably a little bit bigger and nicer to see. We're going to be looking with storm events to do the B-tree index, right? So let's look at we're going to be looking at the state. Let's pretend someone's going to want to query based on state. Like what state? I want to look up storm events in my state. So we're going to make an index on the state column. And the first thing we're going to do is we're going to look at, and this query does it for us, the relative sizes of things before we make an index. So if we do this, we can see that the total size of the column is about 579K, and the table is about 44 megs. There's actually quite a bit of extra space. I learned this in doing this, writing this catacoda, that goes into other things. Making up a table other than the actual data you put in. But anyway, the size of this column is 579K. The average size of an entry is 9.5 bytes. Right, it's varchar or it's text, so it varies depending on the size of the text, and that's about 1% of the table. All right, so let's look at our query speeds before we create an index. Right, so that's going to be doing this. And we can say that it's doing a sequential scan. I did a class on explain analyze, or I did a stream on explain analyze. Basically what explain analyze does is it runs your query and gives you timing on the results. The only one we're really going to pay attention to today is how it's doing it. So it's saying, look, I can't use an index. I'm doing a sequential scan. And the total execution time, which is about 30 milliseconds. And I'll do it, sometimes I find that this changes depending on the state of the database. So let's do it a couple times. So it's somewhere between 27, 38, 44. We're bouncing around up in that area. Okay. Which is also a thing about when you do benchmarking, right? Like do it several times, variability. All right. So the other thing we're going to look at is inserts. And so what I'm going to do here is, and you can see it here, is I'm going to generate IDs between 100,000 and 11,000. I think, is that right? 110,000? No, so I'm going to put in 10,000 entries, and I'm going to put a random ID, like a random text string, into the state name column. It's the text field, so it doesn't care. So I'm going to see how long it takes. And now, what I said in my other explain class is, explain analyze actually means explain execute. So this would actually have inserted the data into the table, which we don't want to do. So we put this inside of a transaction. So we begin, we do the insertions, and then we roll back, right? So we don't actually put the data in. So let's go ahead and do it. And we get that. Putting in 10,000 entries takes about, somewhere between 40 and 60 milliseconds, right? So that's what we're looking at beforehand. Now, let's go ahead and make an index. So this is the syntax for making an index. Create index on, and you say the table name and the column you want to make it on. And remember I said by default, we're going to make a B tree. So let's make a B tree. We don't have much data in there, so creating the index is actually pretty quick. And now if I look at the size of the index, so this is using that slash syntax, di, and then plus is extended information on the index, which matches the index name that we gave it up above. We see that the column size is actually 1 meg or 1.7 megs, right? And if we go back and look at the size of the table, it's the column itself. The size of the column itself was half a meg. So the index size here is 3 times the actual size of the data itself, right? So that is, quite a bit of disk space that you're ending up using right there. Right, good. So now you're seeing that disk trade-off, right? And I think that is one of the main shocking things to people is they don't actually think about, oh, well, the index makes disk space, but that's not going to be that much. Actually, in this case, making that B-tree data structure off of the data that we have is it's 3 times the size of the original data, right? But let's see if the query planner uses it. So we're going to do this one, explain analyze, select, and it's just a normal where state equals New York. And you say, oh, there we go. We got a bitmap index scan using the index, and then it does a heap scan on the index scan. I'm not going to go into, I think I went into what a heap scan is, the index scan, a bitmap index scan is in the explain analyze class. I'm not going to go into it. This is an indication though that we have used the index, right? Because it says I'm using the index. And now we get execution time somewhere between, like once it's warmed up, we're getting execution times of 1 millisecond, right? Whereas before, I think we were around 20 milliseconds or 30 milliseconds. I don't remember exactly. Let's see what the text says. Before an index, we were getting times around 34 milliseconds, right? So this is the 30 times. So for a 3-time increase in disk space it's not 3 times increase. Yeah, it is 3 times increase in disk space. We get a 30-time increase in query time. So if this was an important query to you, that's actually quite an improvement. And I know you're saying, oh, well, it's only 1 versus 30 milliseconds. No one will notice. This is all sample data, right? So don't get too hung up on the exact numbers. It's the relative improvements that you're getting. And again, the relative improvements is going to be highly characteristic depending on your data and stuff like that, right? So, but it's trying to give you an order of magnitude stuff to think about and how to think about some of your data. All right. So you're like, oh, that's cool. So I should always look, the index is going to help me with everything. And the explain analyze, the query planner is always going to use it. No. So here we're going to use it with the less than operator, which should take advantage of the index based on what we knew before, right? So we're saying explain, analyze, select event, blah, 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 where state is less than New York. And so this is going to use alphabetical sorting. So this is going to be any state name that comes before New York in the alphabet. And that's actually a lot of states, right? And so if we go ahead and do that query, let me go back to the bottom here. Actually, let me clear this screen so we get some clarity. There we go. You can see it does a sequential scan again, right? And it's back up to 35 milliseconds. And the reason why it doesn't use the index is because more than 50% of the data in the table is returned in the query, right? So this is way more than above that 5, 10, 15% threshold that we were talking about before. I was talking about. You're not talking. You guys are all silent. Oh, and Randall's that student that shows up and says, sorry, I'm late. Interrupts the whole class to tell everybody that he's late. Thanks, buddy. Thanks a lot. Knew I could count on you for that behavior. Anyway, so what you can see here is the index didn't help. Even though you were always taught, like, indexes help with query speed. It didn't help in this case because we're trying to query on too much of the data. But if we change our query to say where it's greater than Wisconsin, which means basically Wyoming, right? You'll see that it now will use the query, and we get back down to, and if I do it twice, we'll get even faster timings, right? That's just the query planner warming up and starting to cache the query plan. So anyway, you can see now it's using the index again, and so we get that benefit. So again, you put that example in there to make you aware of these trade-offs where, like, don't just make an index and let it be. Like, if you need to speed up a query, make an index, do some typical queries against it using explain analyze, and see if it's actually taking advantage of that index, because you're going to pay for it. And I'm going to show you the next pay for it right here. Let's clear the screen again. Let's see what happens to our inserts. So we're going to insert the same exact inserts again. The only thing that's different now is just that we have an index on the table, right? And so if we do this, well, I get an execution time of 200 milliseconds, right? Or I get an insert time of 95 milliseconds. Again, this is just going to bounce around. So it's somewhere between 95 and 200, right? It's going to take to actually milliseconds to insert another 10,000 records. And so that's somewhere between a 2x to 5x increase in insertion time, right? So if your table is write heavy, and the same, we're going to see something similar with updates as well, right? So inserts and updates both actually create new data values. For those who don't know, the data in Postgres is immutable. Like the data, like once you write something to disk, that's immutable. You don't ever change it. When you're doing an update, you're actually writing a new entry to disk, changing the pointer for where that data value lives from that one disk to the other part of disk. So you don't ever update in place on the data in disk. You just create a new entry. So it's very similar to an insert. So anyway, so you're going to pay, if this is a write heavy table, you're going to pay a lot in terms of insertion speed. So if you're getting bound, and that's going to cost you on CPU too, right? Because the CPU has to go and when it's trying to update the index, it's got to do a lot of work to figure out where that is. So if you're finding that your database is really CPU bound and you don't have very complicated queries that are causing a lot of CPU use, it might actually be that you're trying to write to columns that have indexes on them, right? And that cost is only going to increase if you have more columns with more indices, right? So that's just for adding one column with an index. If I had added like 4 columns, all of them having indices, and I'm updating all 4 of those values with every insert, you're going to really start slowing down your insertions speed, right? So this could argue for something like I have one table that is actually, or one database that's actually for insertions and like my transactional system, and I don't really index very much there. And then I have another table where I do, or another database where I export that nightly or whatever frequency, and then use that for readings, right? So anyway, no, this formatting got messed up here, but you can play around more. This just tells me how to drop the index on that column if I want to, right? And so you can play around with that and play with other things with the index if you want to. All right, let's go on to the next one. So that was B-trees. Any questions from the class, except for Randy, who's late, so he doesn't get to ask. Well, he can ask the first question if he wants. Any questions about B-trees, of course, just pop them in the chat while we're going. But that's B-trees. That's the default one you get, and that's some of the things you're talking about. Some of the trade-offs you're going to make. So the things, again, I want you to understand is trade-offs that you make when making an index, and they don't always speed things up. It just depends. Some of it's going to depend on your characteristics of your data and the index itself. All right. So now let's talk about GIN indexes. So GIN indexes stands for a generalized inverted index. And the purpose of a GIN index is very different from a B tree. There is actually, GIN is a generalized type index. So you can have you can do multiple different types of bindings to it actually. But I got myself down a path I don't actually want to say. Can we rewind that? And ignore that. Zip it. What makes the GIN index very different from the B tree is that you can have multiple keys per row in the index, right? Or for the data. So, for example, with a B tree, we create one and only one entry for that state in the index, so that you can say New York equals, this portion on disk. This entry for New York points to this point on disk. With the GIN index, we can actually have multiple keys in the index pointing to a row, right? And so this makes it really good for things where you have multiple values in a data entry, row, column, / whatever column you're indexing on. You can have multiple values that you point to the same row. So for example, things like that are JSON, right? In JSON, we're generally going through and looking at different key attribute values or name attribute values. And we want to be able to search on those different name attribute values, right? So the big ones that this is used for is with JSON, all the array types, right? So you know how Postgres, or hopefully now you know after I just tell you, that for all the basic data types, Postgres, like integer, character, floats, you can make an array in your column. You can actually store an array of values in there, right? And so that is actually good for GIN indexes because there's multiple values in there. And so we might want to say, there's actually values 3, 7, 5, 12, all in this one row in the array. And so that's the multiple keys per row. And then also full text search, TS vector, right? It actually is good for this as well because we're searching off of multiple things in that free text search, right? So they're composite values. All right. So there is also an extension that allows you to build a B tree index inside the GIN index. And you're like, whoa, what? Why? What are you talking about? So sometimes you make a multi-column index, right? Where you're going to say, I want my user ID plus I want to do free text search on their name or their company name or something like that, right? And so you want to make a dual column index. Postgres has that capabilities. Well, if you say you want to do that using a GIN index because you want to be able to search against the JSON or the free text, and then you put the B tree column in there as well. So you say create index on ID, company name in the index creation. It'll barf at you and say, no, you can't do that. That's I can't use a GIN index on an integer column. And so if you put this extension on, you can actually do that because it'll allow you to create a B tree inside of the GIN index. Okay, so that's what it's for. Multiple column types. All right, so let's see how that works. So the official documentation has a good list of operators and data types that come with a GIN, so I'm not going to list it all here. But what we can do with a GIN index with arrays, that's the examples we're going to focus on, is you can do array equality, array containment. So like, does this array contain this other array, or is this array contained by, that's the next one, or do these arrays overlap? So do they share values in common? That's the overlap, right? Not all of them, but they have overlap between them, right? And any other array operators like equality will not use the index. So that's where I wanted to talk to you about the operators. If you're testing for equalities between arrays, this will not help you. The index will not help you. And so don't make an index hoping to speed up your equals query for arrays. All right, so we're going to use simulated data for this one because it was hard for me to come up with a good example of array data that I have, like sample data sets that have that. So we're just going to create a table. It's got an ID column, int, and it's got an array column called the array, and it's an array of integers inside of it. So let's create the table. Boop. There we go. Now we're going to insert some values in. We're going to create 15,000 entries table, 15,000 entries in the table. And in the array, it's going to be we're going to create a 3-element array, and it's going to contain integers between 0 and 1,000, right? So for each entry, it'll be some random integer between 0 and 1,000. So that's what this query does right here. So we do that. There we go. We inserted 15,000 records. Let's look at the size of the table beforehand. The column is 483K. The average size is exact because an integer should take an exact amount of disks no matter the size of the integer. It always takes the same amount on disk. And the table size is about 1 meg. Right? So about half of it is taken up by our array column. All right. So before an index, it's on every page. It's so annoying. Something went wrong with the. This is going to cause an error. Yeah, but something went wrong with the formatting in the final stages, and I don't know why. Anyway, Control L. All right. Oops, it needs this. No, it needs a single quote to finish it off, and then it needs this. Okay, good. All right, so we're going to go ahead and paste in the select, right? For looking for array. Now, what we're doing here is that's a containment operator. So how many array? We're selecting all the arrays that contain 75. The number 75 in the array, right? So that's a containment query. And so there we go. That's what it looks like. So every one of the arrays that comes back you'll see contains the entry 75, right? And I don't know how 44 of them do, right? Now let's look at the timing of the explain analyze on that, right? So again, there's no index, so it can't index that. And it's taking about 4 milliseconds to do that. Let's do it a couple times. Looking pretty solid between 4 and 6. Well, there's 7, there's 3, right? So somewhere in that range, right? 4. But now I got an execution time of 3.2 when I originally did this. Now let's look at the timing for inserting another 15,000 rows. And it looks like about 20 milliseconds. Let's do it a couple times. Bloop. Bloop, 17, 22. So somewhere between, let's say 18 and 22. Can we agree on that one? Anyway, that's what it's looking like for the insertions, right? So now let's go ahead and create the index. So the way you make this index now has to be different, because if you don't put this word gin on there, you're going to end up with a B tree on that one, which isn't very helpful on an array. You can make it. It won't stop you from, maybe it won't actually. We could try that. Let's try that. I don't think it actually will let you, because it'll say, I don't have a binding between B tree and arrays. But let's make this one first. Bloop. Okay, so we made our normal index. Let's try to make the other one without this. My guess is, and I think I can get rid of, I can actually, well, we can also change this to B tree, right? I think. I've never tried this. This is the fun part about coding together. Yeah. Oh, I got to change the name. It's going to say, no, you can't do that because, oh, it did. Interesting. All right, let's get rid of that. Drop index. I would have thought it would have said, I don't have a binding, but I guess it's saying, well, I guess I'll try to do something. Maybe it does have a binding for arrays. It's just not very helpful. All right, there we go. Oh, you know what? I wonder if the B tree does the equality. I bet you that's what I'm guessing. B tree will actually help you with the array equality. Not a very helpful query though for arrays, just saying. All right. Anyway, now we've got our normal index on there. Sorry for the little aside. Let's look at the size of it though. Right. So this array is 232K. The index, is 232K. So that's 50%, a 50% increase, or is it 50% the size of the original array? Let's see. 483, and we're now at 232. So about half the size, right? So it's not increasing in size. I will caution you though that this one is highly dependent upon the size of the stuff that you're indexing, right? Because you're going to create multiple keys. In this case, we only had 3 entries in there, so that's not very much. If you have like a big blob of JSON or something like that, the index might be smaller, but it actually might be quite a bit larger. So this is one where you definitely want to look at it on the one that you use without a hard and fast rule about how much size you're going to get. All right, now let's look at the query times we get. All right, so now when we look for our array, I got 0.17. I'm not even a full millisecond to look for arrays with 75 in them. And you can see it's using the index now, right? And we can go again, right? So there we go. It's really freaking fast. That's like a 17 times improvement on that query. So if you're using arrays and stuff like that, it really gives you a big speed up. Now, let's look at indexing time though. I mean, insertion. So we're going to again insert another 15,000. And we're also going to look at the changes in table size. I found out you can actually look at the change in the index in the column size from adding those, right? So and compare it to the index size. So let's see how fast they grow together. So the reason I brought this up is because gins grow fast. All right, so now if we're doing the insertions, we're up to 43. I got 45 in there. I had 33 in the last time I ran it. Let's run it again. So if I run it again, I'm somewhere around 33, right? So, which is twice as slow as our non-indexed. That's about twice as slow as our non-indexed. And your index has grown now. Look, so that now we can see the column size is only 900 and it's a meg basically, but our index size has grown to 3 megs. So this is one of the problems with gins. They grow exponentially fast. Right? That's one of the nice parts. B trees, I think, grow logarithmically fast. Gin indexes grow exponentially fast. So it has now grown to be 10. It was 50% to start with. It's now 10 times our size. So they grow very rapidly, which is what I was trying to point out with. We had very small amounts of values with small things in them. The more you put in, the bigger they get. So pay attention to that as you're building your B trees, because they can start eating up disk really rapidly. All right, so there's the trade-off again with a gin. All right, let's go to a gist. And for all my spatial heads on the call, this one should be familiar to you, right? You may not know why it's called a gist. It stands for Generalized Search Tree. I don't know where the I is coming from in gist here and why it's lowercase when we did gin. Oh, I guess it's the same thing. I guess they're doing generalized inverted index. No, I don't even, forget it. I don't even want to figure out where the acronyms come from. Anyway, someone will probably correct me in the chat about why. I'm too, whatever. Anyway, so the purpose for a gist, it's a generalized index. So notice that it's a generalized search tree. So rather than a B tree, this is a very generalized tree. B trees work for things that are sortable, right? And you can do greater than, less than, equal to, where they have a natural sort order, kind of one-dimensional natural sort order. Gist, as long as you can tell me how to make a tree out of it, I'll let you make an index on it, right? So this can be used for things like spatial objects, right? Like we've seen with PostgIS. So we create a tree structure using arbitrary splitting based on a custom operator. So in PostgIS, the gist spatial indexing happens with an R tree under the hood. So the gist is actually relying on the R tree to do the splitting, but then all the indexing and updating and maintaining and using it with the query planner, that's actually implemented by the gist itself, right? And so this is getting into a topic, I think I'll cover it at the end, because I'm going to cover at the end how indices actually, not exactly how, but some of the idea about how they happen under the hoods for Postgres. But I'm going to put that at the end so that we can just get through the examples before filling people's heads with the somewhat harder stuff to conceptually get. All right. So we're going to use the spatial stuff here, right? Again, there's an extension for gist because by default, the only things that, there's, those built-in spatial types in Postgres, not the PostgIS ones. The Postgres ones has some spatial types. By default, that and full text search are the only things that have operators for gist, right? We're not going to use those. But again, if you wanted to do a multi-column, so like let's say you're using PostgIS and you want to use the user ID, again, which is an ID, and then you want to index their zip code, the bounding box for their zip code, right? That's a multi-column index. And what you're going to want to do, again, is use a B tree or something that has an operator for a B tree. And so what you're going to want to use is there's an extension for B tree gist, which allows you to mix this PostgIS polygon type gist index along with the B tree one. So there's an extension if you need to do that. Same idea as the gin one. So in PostGIS, the main operators, there's a couple others, but almost no one ever uses them. But the main operators that can take advantage of the gist index are containment, contains, intersection, and then you can also use it with the nearest neighbor, k nearest neighbors operator. When used in order by, you get efficient nearest neighbor results. So again, if you're not going to do any of those queries with your spatial data, you do not need to make the gist index. I know by default we're told to make the gist index when we do PostGIS, and it can also do these range operators too, right? Range equality, range overlap. Oh, this is for gist indexes also work with range types, right? So Postgres has this built-in thing called ranges where you can put in a date range, and you can actually query like, is a date in this date range? And so you can in one column you have the beginning and the end date of the range, right? It's kind of a fun type as opposed to having two different columns like begin date and end date. You can have a range type that is contains a beginning and an end date. And so this is the operators that work with range, right? And that's kind of fun too. But I think today, I did a spatial one. Yeah, we're doing spatial. So these are the only ones that work. So back to my spatial heads. If you're not doing these operations, you don't actually have to make a gist index. I know that almost all the examples have you making it gist index, but if you're just doing things like, are these two geometries equal? Like equality operator, you will not actually take advantage of the index, and you will chew up disk space, and you will slow down your insertion and all sorts of other fun stuff, right? And use up extra CPU. So be aware of that when you're doing stuff. So we're going to test these out today. And then these are the range ones, and they're really fun. You can full text supports gist, but GIN is the recommended index type, so I don't even go into it. All right. So our table that we're going to look at is all the county polygons for the United States. And I'm going to first drop the indexes because they already exist. And so that's no fun if they're already there. Right, so we drop the indexes. Again, let's look at the size. Let's look at the size. I need to go back and reformat all these. Right, so the geometry column is 120 megabytes out of the 127 megabyte table. Right, so obviously the polygon geometries are taking up a lot of the disk space in that table. There's not much else in that table. If you want me to show you geometry, right? There's a bunch of other columns. There's basically like the FIPS number and the name and the GeoID and all sorts of other stuff. And the interior, there's a geography column point, and there's also a geography column. The one that's taking up most of the space, the one we're going to be working with today, is the outline boundary, and it's a geography of multi-polygon, and so it takes up a lot of the space of the table. Yes, I know that it's called the geom, even though I'm using a geography type. Come at me. All right. Anyway, let's see. Oh, and here's the one for I also have another one for looking at the size of the point column. That's only 92K of the 127, and that makes sense because a point geometry just only has an X and a Y, right? A long and a lat. So that doesn't actually take up much space. Polygons, on the other hand, have lots of points usually making up their boundaries. So that's why they have lots of XYs inside of them. So that's why they take up a lot of space. All right. I know we're going long, but you asked for this. Lateral queries would have been much shorter. Lateral joins would have been much shorter. All right. So let's see. Let's do an explain, analyze. We're going to select. We are going to find we're going to do two different queries. We're going to find, this is the geographic center of the United States, and we're going to find the 10 closest interior points, the point columns, this interior point one up here. We're going to find the 10 closest points to the geographic center of the United States. Right? So, and we're going to see how long that takes. So that takes about 8 milliseconds, 11, somewhere between 7 and 11. It looks like around 8, right? We'll say 8. And then we're going to do my home county where I grew up, and we're going to search the bordering counties of Rockland County, including Rockland County itself, right? So there we're going to be using the intersection operator. So the other one we were using the k nearest neighbor operator right there. And this one we're going to be using the intersection operator. So let's go ahead and do that one. right? And that takes about 30 milliseconds. Do you want to see all the counties that border my state? No one's probably paying attention, so I'm going to get to do it anyway. You don't even have to ask you. Let's just go up here. So I'm using actually a CTE here as well. It's exciting, but I'm not going to explain that today. There, Westchester, Putnam, Bergen, Passaic, Rockland, and then Orange. My sister lives in Orange County. All right. Anyway, should we keep going? Let's keep going. Now let's insert. I'm not going to insert random geometry polygons. That's just too hard to actually do well. So what I do is I'm inserting random points somewhere in the Western Hemisphere. Actually, the Northwestern Hemispheres or quarter sphere, whatever you call it. Anyway, we're going to insert 5,000 random points anywhere in that hemisphere. And that takes about somewhere between 30 and 45. No, there's a 50. So let's just say 45 milliseconds. 45 milliseconds to do. All right. Now, let's create the index. So we're going to create, now doing this one is just as simple as saying gist and on the columns that we want. So very similar, except now we just say gist rather than gin. And we're going to get both of those indexes, right? Indices. Now, let's run our top 10 counties, right? And we get 1 millisecond, less than a millisecond, right? So in this case, we're almost 10 times faster, an order of magnitude faster in terms of doing that query now that we have the index to take advantage of. And as Paul Ramsey has pointed out in other places, this nearest neighbor operator scales really, really well using the bounding boxes. Like it doesn't, no matter how many more features you add, it doesn't scale, it scales less than linearly. So it's probably logarithmic with the number of features that you add in terms of how it slows down. So it's really good that way. So that's a cool one. That's great. We got an order of magnitude increase in our search. And then let's look at our Rockland County one. So it's now actually under a millisecond to do an intersection of boundaries, right? Which is 30 times faster the original query time. So huge increases in performance by using the gist index on our geometry types, or geography types in this case. But if we look at inserts, we can see that it actually is quite a bit slower, right? It is now at 70 milliseconds, 90, somewhere around there, right? So we've almost doubled our insertion time, all right, 100. So it's a lot slower to do that. Did I actually look at the size increase after I made the... I didn't. Let's look at how much bigger our table is now that we've... let's look at the county geometry one. Let's look at... Oh, we wanted to do... let's do the first look at the... right. This is that whole big long one. Let's look at the polygon one. That one would probably be the biggest. Yeah, I know. Let's get rid of all that on the screen. So, and oh, we wanted to look at the index size. What's the size? What do we call that? What do we call that index? Anybody remember? County geometry index. Let's look at that. There we go. What? So it's 2 megs in size. So not that big compared. And that makes sense, right? Because what we for those of you who know, when we make an index, a gist index on polygons, we're basically reducing all that complexity in the polygon to a bounding box. Right? And so there's only 4 points in that. So it's a lot smaller in this case. So the way you take away from this is it highly depends on the indexing scheme, like what it's actually doing under the hoods to create that gist index. In this case, for a gist, it's going to, in general, be much smaller, especially for, actually it'll be larger. That'll be fun. Let's actually change that to the, what was the name of the index for the, creating the index for the geometry interior point, right? Let's look at that one. That one actually should be larger because I think we've created a interior underscore PNT. It should be larger because we're actually creating a bounding box for a point. Yeah, so that's actually 2 megs in size. when the original, if we go back up and we look at the original, oh, now I gotta somehow do this one. The original was 92K. So we've actually created more disk space doing the point one because we created a bounding box for each point. So your results may vary depending on your data type. What I've been saying all along. You can't just make an index and let it sit there and assume that it's doing good stuff for you. All right, last type. This is a special one that most people don't know about, and it's only for really specialized use cases, but it turns out this specialized use case is quite a common use case. So it's specialized, but it's quite common. So a Brin index stands for block range index, right? And what that means is the index is actually indexing what's actually written on disk. It doesn't even so much look at the data values, like point to individual data values. It's looking at, here's a block of data, and I'm going to index what's inside the blocks of data. And so here's the things that the only reasons you would use a Brin. It's got to have a very large table. So probably at least 1 million rows. Inserts and reads only. Literally, inserts and reads only. So updates or deletes actually quickly ruin a Brin index. And the column you want, and this is the most important part. Well, actually, these are all most important. Actually, the last two are the most important. The first one is you can put it there. It doesn't do as much damage, but it probably won't be used. The third one, though, is the column you want to index is inserted in order on the column you want to index, right? The column you want to index is inserted in order. So Brin index relies on related data being written close together on disk. So that's what I was saying before is like, so say for example, you pipe your logs to a table. Well, most log statements have a timestamp on them, right? And you usually are going to want to search on the timestamps. Like I want to see all the logs between this time and this time, or I want to see the logs on this day, or I want to do something like that, right? So what that means is when the data is inserted, timestamps should increase or decrease, whatever you want to insert it. I don't know what, but basically they have to be in order, right? And so what that means is the way the Brin index works is it says, okay, when I wrote the data on disk, starting at this block to this range of other blocks, it starts at this value and it ends at this value. And then I go to the next one, and it doesn't even say it ends. It just says basically it starts. No, it does say the range, I think. Yeah. It says from this to this, this range contains from this to this, and this range contains from this to this. And it's assumed that inside of that range, it's increasing, right? And that's why updates and deletes mess things up, because if you update and delete data, remember I said that if you update data, it actually doesn't rewrite into that same spot. It actually removes that one and then inserts it into some new spot. And then it may write stuff back into that other place on disk later, depending on how like after vacuums and stuff. So then it messes up what's inside the range. And this index is going to rely on that range being continuous, right? And so this is really good for like log files, financial transactions, data feeds from IoT sensors, right? Those kinds of things where they have a timestamp or an increasing number. Like this is entry 1, entry 2, entry 3, your journal. You're going to write over 1 million rows, right? But those kinds of things, and you can't edit your journal, Twitter, maybe, I don't know. Anyway, those kinds of things make it very fast to do these searches, right? And this goes into a little bit more of the details. The operators, so there's it ships with a bunch of operators for this. You can actually use it for internet ranges even. I mean, it ships for almost all the built-in data types. You can make a Brin index on almost every data type, but there's a fun one. It even has one for like for internet addresses. If you store INET addresses in your table, there's an INET data type for Postgres. You can actually it will work with questions of containment as well because the data is in order, right? So it'll look for questions of containment and other things. But we're not going to do that today. We're going to actually, again, that would mean your internet addresses are inserted in order. So that seems kind of weird. But you can also use Brin indexes with range types and get most of the same operators we saw with gist. But it assumes that your ranges are inserted in order, which is kind of weird as well, and don't get updated or deleted. Right. So we're just going to actually insert, I think, is that how much? $1 million? $1 million, we're going to insert just 1 to 1 million. Right? That's what our table is going to be. Again, if you have questions, drop it in the chat. So here we go. we're going to insert, we inserted 1 million data values. So we just made a table with 1 million indices in them. No primary key, just straight up one column, 1 to 1 million in the data. Now let's look at the table size, right? Why is that one okay? I don't know. Whatever. The average size is 4 bytes. Makes sense. That's 4 bytes is for an integer. It's 4 megs for that column, right? But notice this is what I was saying. There's a bunch of other data stored in the table. There's only one column. It's 4 megs, but the table size is 35 megs. Anyway, let's do a query looking for the ID equal to 99,000, right? So let's do explain analyze. That takes 129 milliseconds, right? So 143. And that's because we have to scan through 1 million records until we hit 99,000. Because this, and it's doing it a parallel sequential, but it's still doing a sequential scan. Or it's doing a sequential scan. Maybe it split the sequence in half and is looking for both halves. I don't know exactly how that works. But what it's basically doing is saying, look, I can't, I have to basically scan through the whole table until I find 99,000. So, and it's not making any assumption about them being in order. So it can't do anything. And let's look at adding another 1 million rows and how long it takes. Right. So it takes about a second, almost a second to, a second there to insert another 1 million rows and generate random numbers. Right. So now we're going to create the Brin index and we're going to say Brin and it's on the ID column, which is what we said it was going to be. Right. And so what was the size of that column again? That size of that column was 4 megs. If you look at the size of the index, it's going to be very small. Oops, I gotta scroll all the way down. It's only 48K, right? On 4 megs of data. Or was it 4 megs of data? Yeah, I get it, whatever. Because, and the reason is because for each, depending on how much data it can fit in that block, it's not just even a block, it's a block range. So a range of blocks. And so all it's storing for that block range, it's got some small little binary Boolean stuff that it puts in there. But the main things it's storing is, here's the number that's at the beginning of this block range. And the beginning of this block range is this value. And it points to this place on disk and it goes to the other place, right? So it's just holding a very small amount of data to index all those values. And now if we look at our query to look for 99,000, it's 9 milliseconds. Right? So which is, there's 3, right? And there's 5. So we're basically almost an order of magnitude faster looking, because now it can use that index to find. So what it does is it goes, oh, this beginning of this range is less than that value. It's probably, and this one above it is above it. So it's somewhere in this block range. Now I'm going to sequentially scan this block range, right? So it does a sequential scan, but it does it on a much, much, much smaller part of the disk. And that's how block range works. That's how this works, right? So let's look at insert speeds. So inserts should be much faster as well. It's only 50%. It's another, that one. Well, let's look at the second one. Yeah, it's like doubling of the insert speeds, right? We're almost, or a little bit over doubling, because it was about a second. There, that one's a little bit less than doubling. So it's somewhere between a little bit less than doubling and a doubling. Okay. All right. And then I want to show you something. So one of the things you can do with block range indexes or Brins is you can change how big the range is. So remember I said it starts with this block and it ends with this block. By default, we do 128 blocks, right? And you can actually make it smaller and say, look, by default, I want you to create an index entry. And in this case, we're going to make it for only 4 blocks. So every 4 blocks, make a new index entry, right? And so when we do that, so we drop that index, make a new one, and do the new query, we get our query times down to, well, let me do it again one more time. Oops, rats. I don't want to drop and then recreate it each time. Let me just do the explain analyze part again. Right? It's down to, it's not actually getting that much faster. When I did it before, I got it down, it's actually slower for the query. That's weird. When I was doing this before, my search time went from 6 milliseconds to 0.9 milliseconds. And that's because it's faster for it to read through the index, find the block that it wants, and then it has to scan less blocks to actually find the index size. You can play around with this. I don't know why it's slower. Did it actually make the index? And what's the index size on this one? It'll be a little bit larger, right? So if I do slash, because we're creating more entries, but it only goes up to 64 megs. Okay, sorry. Brin. I forgot the plus, not an underscore. Right. It's 184K. Oh, something weird's going on. I don't know what happened there. Did I actually roll back the insertions? I'm wondering if I didn't roll back those insertions. Anyway, because go through the exercise and for yourself and see if it works. So that's the case for a Brin. I don't think most people know about it, but it helps a lot and it doesn't add a lot of disk space. So it's really awesome for very specific use cases that come up a lot. Like you're doing images coming off of a drone, right? Those are usually coming in timestamp order. You can, and if you sort by that, you can say, I want the image that happened at this time, GPS fixes, all that stuff. Anyway, so that's all the indexes. We did btree, gin, gist, and Brin. I'm kind of done. The last thing, though, that I do want to talk about, I know we're at an hour. I mean, you should read it. The thing that's interesting, let me go to this. Let me go just to me. I won't talk about it there. The thing is, here's the thing with indexes in Postgres. They're all runtime bindable, right? So, and we saw that with PostGIS. If by default, PostgreSQL doesn't ship with the PostGIS data types indices with gist. And so what happens is when we install the extension, we say, hey, here's some data types, our spatial data types, the geometries and geographies. And then here's how you bind them to a gist index. And the reason we don't see this that often is because by default, Postgres ships with all the default a B tree binding for all the default data types, right? You could actually, if you'd made a new data type, you could ship it as an extension or however you want to install, or as just a new data type that you compile in or something, and you can ship it with a B tree operator, and then you can use it with a B tree. But you could also ship it with a gist operator or a gin operator, and then you could use that data type with a gin or a gist. By default, Postgres ships with all the B tree ones, and so we don't ever have to think about that stuff. But if you start digging in more to indices and how they're used and all that stuff, you're going to need to learn it about bindings, runtime bindings, operators, op classes, all that stuff. I discuss it in the beginning of that index class. If you don't want to get into it, just let that stuff wash over you when you do the class. I'm done. Oh, yeah, Naomi, I have a question about B tree. Go for it, Naomi. I may not be able to answer it, but we can try. Actually, I think it goes faster if I say it here. Go, Naomi, go. I'll take a sip of some detox in the meantime. Oh, so Naomi's question is, how does Postgres know if it's going to be more than 10% or not? Interesting, Naomi. So underneath the hoods, and I wish I knew Postgres better because then I would just whip out the queries to show you. But underneath the hoods, Postgres maintains a table of statistics about each of its tables. So it maintains statistics, like it maintains a distribution. What are the distinct values? All that kind of stuff. And the counts of all those values for each table underneath the hoods. And if you do Google searches on this, you can totally find it. And so the query planner looks at that table to make guesses about how to do the query. And so it's going to look and say, oh, look, here's the range of values and here's how they're sorted. And so I'm going to this is definitely going to return more than 50% of my data. I'm not going to use that when I make my query. So that, I don't know if that helps, right? It's going to do that's why when we see these explain analyzes, actually, let me go back and show you something. Hold on while we load the data. But that's why when you see there's a query, like there's this query planning time, that's the query planner actually going and reading the table stats and figuring out how it's going to actually execute the query. That's the other reason why sometimes fixing your query can be as simple as running analyze on the column, or vacuum analyze, right? So clear up the dead space and reanalyze that column. That's especially why you do it after you create. I probably should have done it after I created each and every one of my indexes. That might be why we're seeing the slow initial query and then the faster second one. It may do a reanalyze in the time. But that's also especially like when you do a bunch of bulk insertions or bulk deletions or updates, you should definitely run analyze again because that'll update the query statistics. And in my explain analyze class, I talk about that a little bit too. About let's do this. Let's just do the create an index. Right. All right. So we created the index, and we'll do the explain analyze. Right. So there's that planning time. That's probably when it's going and looking at the table, right, and saying what is this going to work or not. The other thing though is where is it? There was one statistic. Where was it? I think it has something to do with, if I can't remember off the top of my head. It's been months since I've done that explain analyze class. But there's something about like, I can't remember where it is. There's something in terms of the actual time versus the cost somewhere there where it's basically telling you whether, we were close or we were not close and close to our estimates. And if someone in the chat remembers what I said on that one, but there is a place in the explain analyze where it'll say, I estimated let's actually see if we do this. Actually, I think if I get rid of analyze, let's see if it does that. Right. No, it has to be analyze because it has to see. Yeah. Oh, I think it's actually the difference between the number of rows and the estimated number of rows and the actual number of rows. I keep looking over here because this is where chat is. So I'm talking to you over here, Naomi. If there's a large difference between these two numbers, that means the query planner is way off. And let's actually, you know what? Everybody can go if they want. I'll just do this for Naomi. This is usually what I do in a talk. So let's actually do this. Let's see if it'll work. I think actually it'll work better. Yeah, let's do it here. Let's try it with this one. I'm going to insert you know how I was doing all those insertions with a rollback before? So let's insert a bunch, and then let's insert. Okay, then let's do I want to do this one. We'll do it without the. I don't know. I don't remember which way I should do this, but because I'm trying to think too fast on the fly, and I'm already kind of. But let's do this, right? So it thought it was bringing back 70. It should bring back 79. It actually brought back 52, right? So now if I insert, let's insert a bunch more, and let's run that explain analyze again. No, it's still pretty good, right? It's still pretty close. It's within but it's getting more and more off. Let's see if I run analyze. What's it called? My arrays. Okay, and if we run it again, let's see if it does any better. Yeah, see that? See how it got better after I ran analyze? You can't see my screen. Oh, what the? I'm sitting here talking, and I keep forgetting that. There we go. Sorry, everybody. Of course you can see. So what I did, you want me to do it again? Let me just do it again. Let's just do that again. Let's drop the table. Drop table my array. Okay. Oh yeah. That's Miari. There we go. What? What's the name of the table? My arrays? Steven. Really? Okay. So the table's gone. So let's do this whole exercise again. So now I'm going to demonstrate the whole analyze thing. All right, ready? So we're going to insert. Oh, I got to create the table first. Okay, really ready this time? Okay, now I created the table. Now I'm going to insert 15. I inserted 15,000 arrays, right? And we're going to do the explain analyze on that. Okay, so you can see it thought it should return, it was going to return 79 rows, and then it actually returned 54, right? But now let's go ahead and insert another, I don't know how, 5 times 50, 5 times 15, whatever that is off the top of my, I can't do. And now if we go back up and look at the explain analyze, right, it thinks it's going to return 240. It actually turned 254. This time the estimate's still good. Of course, I wasn't showing the good time. Let's insert a bunch more. Okay, now we got a bunch in there. Let's do the... All right. It thinks it's going to... it's still staying good. Blah. It 800 and it actually returned 860. I think though, like if I now make the... if I now actually do analyze my arrays, right? So now it went through and updated those statistics on the table, and I do this. Didn't do any better. It returned 820. It thinks it's going to return 820, and it brought it closer together. The first time I did this, when nobody was looking, it was off by like 200, and then it was actually off by 5. Of course. We can do it with any of the other ones where we insert a ton of values. Did we insert a lot in the gist? Yeah, we could do that. You want to do that with the gist? I'll do it for the gist. I feel bad because it was so good before and now it's not. It makes me sad. Let's actually... I don't need to drop the index. It doesn't matter. Let's just do the whole... we did it with just the points, right? So let's go ahead and do this one. Right? And so it thinks it's going to... Oh, I did a limit 10. It thinks it's going to return 3,000. It actually returned 10. Huh. I wonder if I actually do an analyze then, right now. Right, so that estimate's off, but that also could be because we're using a bounding box stuff, but I don't know. What was the name of this? Oh, county geometry? County, is that what it's called? County geometry, yeah. Let's see. Okay, and let's see if that changes the... No, it still thinks it's doing 3,000. It's already been analyzed. So I don't... Yeah, that makes me sad. Let's insert... That could be because we have the index. Let's actually... See. No, I don't know. You know what? I hate that I wasn't sharing my screen. We can try it with the Brin. That one had a lot. Let's try it with the Brin. All right, let's do this. 1 million entries in it. And let's do the explain analyze. And it actually brings back 1. It thinks it's going to bring back 5,642. Let's see what happens even if we just analyze. Oops. Bring me, right? This is the last effort because I'm going to let people go. Yeah. See that? Now it thinks it's only going to return 1. And it actually returns 1. See the difference there? So 5642 versus... No, it does not. So yeah, no. Naomi asks. Naomi asked, is it gonna go try to do a index scan, or try to do a full sequential or an index or something? Like actually, what it would do, Naomi, in that case is try an index scan, realize it's getting more than 10% of the values, and then give up. Then that's not what it does at all. Once it's committed to a query, so quick to know also besides the stat table is the query plan. When you execute a query, the query planner goes through a whole, because there's a gazillion different ways. That's a technical term, gazillion. There's a gazillion different ways it can actually choose to do the query and get the same exact results, right? There's a lot of different patterns it can use to get to those same results. And so what the query planner is doing is it's saying, okay, I'm going to try to quickly prune that tree of possible query patterns that I can use to get to the optimal one. And sometimes it's wrong. There's a whole part of Postgres that if you go to look it up that talks about tricking the query planner or ways to tune the query planner. So once it makes its plan, it does the plan. It doesn't ever go into, unless the only thing that would make it stop its query fast sooner than it would is if you have a limit, right? So in a limit, it says I'm only supposed to get 10. I've got 10, I'm done, right? I don't have to finish all of my top 10 stuff. I'm just going to stop when I'm done. And that might be why when we did the limit 10 on the k-nearest neighbors, it's off. there's probably 3,000 that are close, but we told it to stop at 10, and so it stopped, right? So, 3,000 is probably all the 3,000 is all the polygons or all the points, and so yeah, that's exactly why it stops at 10 and it was off. Duh, Steve. Anyway, that's why it's not a good example. All right, so we're done. And next stream will almost definitely be on lateral joins, which are really cool. And I just wrote a blog post and there's a catacoda about them. Thanks for sticking with me for over an hour today. This was a long one. You guys are troopers. I appreciate it. Thanks, everybody. I'll catch you on the flip side. Sweating, though, because it's going to be so hot. I'm so sad.